Okay, hello. Does everyone hear me? Hello?
Yes, I can hear you.
Okay, perfect. Do you see the screen I'm sharing?
Vector geometry.
Yeah. Okay, so let's look at the syllabus first. So if you look at the announcement that I posted, there's a link to archive and you should see like homeworks there. I'm not choosing which homeworks to give you. I do choose the due date and I'm going to try to, I think the first one is like the 28th. So if you have any questions about that, email me, we can talk about it. But so you have homework, then there are going to be a bunch of exams. They're going to be fairly short, like 45 minutes, and I believe there'll be like 4 sections throughout the day, 4 time periods, so different people can take it depending on where they are. What else? People cheated apparently last final, and the last class. People cheated a bunch of times, so just asking questions on Chegg. So yeah, we're gonna try to make sure that doesn't happen again. So yeah, please try not to cheat. You can you should try to do the homework by yourself. Definitely take the test by yourself. So yeah, we're gonna talk more about the exams as that time approaches. Please read the syllabus. If you have any questions, let me know, and we are gonna find a time to talk about it. I'm not going to have any specific office hours. If you want to meet to talk about questions or about the class, email me and we will be able to find the time to do that. Any questions so far? Okay, yeah, so just take a look at the syllabus, and if you have any questions, let me know. So the way I'm going to structure this lecture is I'm basically going to go through the textbook and I'm going to comment, write notes on the side. If I need to, I'm going to go to a whiteboard and write notes there. Please ask questions if you have any. There should be lectures on archive if you want to have a more detailed classical lecture, but I'm not, there's so many resources on that. I'm not going to focus on that. I'm just going to read through the textbook, try to explain what's going on. A lot of the course is focused on the textbook, like the homeworks and all that. It's just one big class. So I think that this will make sense. Okay, so let's begin. So vectors are, how many of you have seen vectors? I'm sure a bunch of you have seen vectors so far, right? Hello?
So yeah.
Yeah. So we're gonna, I guess, have you seen like dot products and cross products?
Yep, E&M course in physics is probably where I first saw this.
Oh yeah. So anyone who's taken physics will know a lot of this. I'm gonna try to go through it quickly. So what are vectors? 1 second. So let's say we have the XY plane over here. So you can think of a vector as having some origin, some direction, and a certain length. So this is a vector. We can call it V. So this is the vector V. And you can translate vectors. So this is the same vector, let's imagine. I mean, it's a little longer, but translated, and those vectors are pretty much equivalent. We don't really care where the origin of a vector is. We only care about its direction and its length, and then we specify the origin when we need to. So generally, if you have 2 points P and Q, so you can imagine that this point is the point P and this point is the point Q. So P has 2 coordinates. Let's say that P is equal to, do they have anything? Fine, AB. So that's what P is. So P is at AB. So that's this point over here. And then Q over here, let's say is CD. And then there's a vector between them. So the vector V is the vector starting at P and going to Q, and we put a little line on it. So that's what V is. V is equal to PQ. And it's the vector starting at P and going to Q. And we're going to see how to find the vector V. So, so in these pictures, we have two vectors. We have this vector over here. It starts at P, which is 2, 2, and it goes to Q, which is at 7, 5. And then you just have a vector between them. And then over here, you have another vector that starts at the origin and goes to R. And R is the point 3, 5. So here are two vectors. Any questions so far? Okay. So generally, like I said, we don't really care about the origin of the vector. So the vector V here and the vector W, they have the same length, they have the same direction. One of them is just the translation of the other. So you just move where the origin is. So these vectors are considered to be equivalent. These vectors are also pretty much equivalent, except for one of them is going the other way. So if you have a vector V and you want to look at the vector having the same direction, but just going in the other direction, or having opposite direction, but the same length, then you look, if this is V, this vector over here will be negative V. So this is negative, what's happening? Negative V. Sorry about that. So, yeah, so again, we don't care about the origin of the vectors. We just care about their direction and their length. So again, we have a few pictures over here. All of the vectors over here are equivalent because they're just translations of each other. These vectors are not. Some of them are pointing in different directions. These vectors are also equivalent, but one's just a translation of V or a translation of V naught to V. So like I said, when you have 2 points, you have the point P, which is A1, B1, and you have the point Q, which is A2, B2. So here, P is equal to the point A1, B1, and Q is equal to the point A2, B2. And I'm putting open parentheses over here to show that there are points in the graph. So here's the point P, and here's the point Q. Now I want to find V, which is the vector between P and Q, starting in P and going to Q. So it starts from P over here, and it goes to Q. And this will be equal to A. So in the first component, you put A2 minus A1. And in the second component, you put B2 minus B1. And the reason for this, well, you can look at the picture over here. What is, so, and this we're going to call AB. So what is A over here? A is A2 minus A1. It's this over here. So it's the amount that we want to go in the X direction. Starting from this point in the X direction, we want to go that amount. And so that's why we look at A2 minus A1. And then B, which is B2 minus B1, is the amount that we want to go in the Y direction, B2 minus B1. And so then V will be the vector where in the X direction we have A, and in the Y direction we have B. And we then denote that new vector. So this should actually be kind of a little sharp. So when you have points like P and Q, we don't want to think about them as vectors. We just want to think about them as points in the plane. We put open parentheses. But when we're talking about vectors, we generally try to put pointy parentheses. And so this is just how we find the vector between 2 points. Okay, any questions? No? Okay. So the resulting vector is the vector V with component A and component B. the magnitude of this vector is going to be the square root of a squared plus b squared. And that just comes from Pythagorean theorem. If here is my vector, this is my vector v, is equal to ab. In order to find the length of this vector, I need to imagine that there's a triangle over here, and this is A, and that's B. So the magnitude of this vector is going to be the square root. So let's go here for a second. So if V is my vector, AB. So now I have a triangle. Let's just put it at the origin. And this over here is the point AB, because it starts from the origin and it goes to this point. So this over here has length A, and this over here has length B. So the magnitude of my vector is going to be equal to the square root of A squared plus B squared. So this squared plus this squared, that gives you the length of your vector. Okay. And so, yeah, so that's this equation over here. Sorry, important to know. The zero vector is just a vector at 0, 0, which has no direction and no magnitude. Like I said, the negative just flips your vector. So if you're going in the AB direction, the negative of that will just flip you. So again, let's imagine that this is your vector with AB. And now let's look at negative V. And for the negative, we just put the negative in each component individually. So this is going to be negative A, negative B. So the negative A tells us to go in this direction, negative A amount, and the negative B tells us to go down. So we're going to have a vector going down with the same magnitude. So a little longer, but going in the opposite direction of this vector. So that's what the negative does. Okay, so over here they're going to ask for an example. They want us to do this example. So that so they want us to see whether V1 and V2 are equivalent, where P1 is equal to this point. So this is the vector V1. Here is P1, and I want to look at the vector from P1 to Q1. So at this vector, and the second vector, here's V2, goes from P2 over here all the way to Q2. So in order to figure out whether these vectors are equivalent, I just need to know whether their components are the same. And so I need to find these vectors. So V1, we know, which is P1, Q1, vector between them, is going to be equal to the component, this is A2 minus A1, so 6 minus 3 in the first component. And then in the second component, we are going to have 5, B2 minus B1, minus 7. So 5 minus 7, which is going to be equal to 3 minus 2. So that's the first vector. Now we just need to figure out what V2 is. Okay, so V2, which is equal to Q2, P2 to Q2, that's going to be equal to, so we're going to look at our A2, which is 2 minus minus 1, which is 3. So this is going to be 3. And then 1 minus 4, which is negative 3. So these two vectors are going to be different. We can even see they're not really, they don't look parallel, V1 and V2 over here. And they do have also different lengths. So that's another reason why they're not equivalent. So then they ask us, what is the magnitude of V1? So here's V1, this is our vector. So we just need to look at 3 squared, so 3, negative 2. Okay, so our vector is the vector 3, -2. Its magnitude is going to be equal to the square root of 3 squared, which is 9. Okay, 3 squared plus -2 squared. Right, that's going to be the magnitude. And this is going to give us the square root of 9 plus 4, which is the square root of 13. So that's what the magnitude is. Yeah, so far so good. Hello? Hey, are there any questions? Hello?
You're good so far. One question I did have was, can we like trust that most of the pictures will be like correct, like or to scale in this textbook?
Yeah, I mean, yeah. The picture should be to scale. If there's a picture that's not to scale, I'll point it out. We
Okay.
will be basically using all these figures, so we'll talk about it. Yeah.
Thank you.
So now the second example, they want us to sketch the vector v, but based at p, which is 1, 4, and we want the same exact vector at the origin. So they basically do that over here for us. P is 1, 4, so that's over here, 1, 4. And then the vector v over here is going to go 2 in the x direction and -3 in the y direction. So we end up at 3, 1. And then if you translate it to the origin, obviously you're going to end up with the vector 2, -3, because that's your vector over here, 2, -3. So, okay. So now when it comes to adding vectors geometrically, we know, we're going to see in a second, that if you have a vector v, so a second. If you have a vector v, which is equal to AB, and you have the vector w, which is equal to CD, then v plus w is going to be equal to a plus c, b plus d. So you just add the components. Now, geometrically, there is another intuition for adding vectors, and the best way to think about it, you see, we want to think about when we add two vectors that they have the same origin, and this is the vector v and this is the vector w. But it's easier to think about it as translating w to some w prime over here and thinking about adding the second vector to the end of the first vector and putting that origin there and then drawing our w there, although now it's w prime because it was translated. And then the vector v plus w will just be that new vector that starts at where v starts and ends where w prime ends. And so then here's a picture that we can look at, which is if this is v and this is w, when you add them, you could either add the w to the tip of v, or you can add v to the tip of w, or you can just think about w here, v here, make a parallelogram and draw this diagonal, and that will be v plus w. So here's a picture. We want to add all these vectors. Well, we can just add one, and then to its tip we add another, and then we add another and another, and that's how we get our vector v, which is the final result of this sum. Okay, what happens if we multiply the vector by a scalar lambda? So let's say I have a vector v, which is AB. Now I want to look at lambda v, and lambda is some constant. So this is the same as just putting lambda in each component, which is the same also as stretching v. You have a vector, you're looking at the vector in the same direction. So here's your vector v, but now you just multiply it, let's say lambda is 2, you just double it. And if it's 1/2, you just do a half, because you're multiplying each component. If lambda is 0, you end up with the 0 vector. And if lambda is negative, you start going in the other direction. Now, what is the magnitude of lambda v? Well, this is the same as the square root of lambda a squared plus lambda b squared. And this is going to be the same as the square root of lambda squared a squared plus b squared. And this is going to be the same as the absolute value of lambda times the magnitude, well, times the square root of a squared plus b squared, which is going to be equal to the absolute value of lambda times the magnitude of v. So going back to the book, if you multiply a vector by a scalar, it will then have length absolute value of v times the original magnitude. If lambda is positive, it will point in the same direction as the original vector, v. So like I said, if here's my v, and my lambda is positive, I'm going to be some scale of this, but I'm going to be in the same direction. And if lambda is negative, I'm going to be going negative. So now I'm pointing in the opposite direction. Okay. So we end up with this equation, which is easy to derive, like I said, and this picture, which is, well, here's your v. It has 2, I guess it's 2, 3. And then if you multiply it by 2, you double it. If the negative one is in the opposite direction. Now this is 6 and this is 4, because you multiplied each component. So v over here is equal to 3, 2. And now if you, so 2v is going to be equal to 6, 4. You multiply each component. So when you multiply this component, you double it. When you multiply this component, you double it. So you get a vector twice as long. And then talking about subtraction, when we take v minus w, well, now that we know about constants, we can say that this is equal to v plus negative w. So we can use the rules about plus, and the negative is just flipping the w. So 1 second. Okay. 1 second. So far, are there any questions? Okay, so here's my v, and here's my w. And now my negative w will just be the opposite of that. And so I can think about this over here, and I can move it over here, right? So now the v minus w, or really v plus minus w, is going to give us v minus w. Okay, so if here's my w and here is my v, then again, this over here is my negative w. And 1 second. Yeah, then I can move this over here. Okay, a little smaller. So now here is my negative w. So here is my v minus w, and then I can translate that here, and I can get that. Okay, so that's just how subtraction works. But again, subtraction in components, you can just subtract each component. Same thing that we did for addition, you're just going to do for subtracting. So in terms of computing, you don't really need to understand the geometric idea behind addition. Addition is important. Subtraction is a little less, but in terms of the components, again, if you have v is equal to ab, and W is equal to CD, then V minus W is going to be equal to A minus C and B minus D. Okay, so you just subtract the components. Okay. So here are two pictures that try to explain, this tries to explain addition of vectors, and this tries to explain scalar multiplication. So again, scalar multiplication, you just multiply the x direction by lambda and the y direction by lambda, and you end up with your v lambda. When does this class end?
11:25.
Oh yeah, perfect, thank you. Okay, and in terms of addition over here, so here's my V, here's my W. They try to show how adding the different components. D over here, you add your D and you add your, well, I'm not really sure that this matters, but where is your B? Okay, oh right, you see to your B over here, that's over here, you add your D. Anyway, picture doesn't really matter that much, but over here we have the equations. V plus W, if V is AB and W is CD, then V plus W is A plus C, V plus D, V minus W is A minus C, and B minus D. If you multiply by a constant, you just put the constant in each component, and the last rule doesn't really matter. And then this over here is not really like relevant, I don't think, so it doesn't really matter. And okay, here we have an example. So you have the vector V and you have your vector W, and they want you to calculate V plus W. So V plus W is going to be equal to 1, 4 plus 3, 2, which is going to be equal to 1 plus 3, and then 4 plus 2, which is 4, 6. And then when you multiply by 5, you just put it inside and you get 5, 20. Okay. So here are some basic properties of vector addition. And it works also for subtraction, at least some of these do. But commutative does, well, not. But commutative law for addition, V plus W is equal to W plus V. And the way to see this is that, again, okay. So if V is equal to A, let's say V is equal to V1 and V2, and then W, okay, W is equal to W1 and W2. Then V plus W is going to be equal to V1 plus W1, V2 plus W2, which is going to be equal, and now each one of these can commute because these are just scalars, so this is W1 plus V1, and this is W2 plus V2, and this is just W plus V. So V plus W is equal to W plus V. And that's how you see the first part, and this is just, you see commutativity of real numbers. If you have a scalar here, it distributes, but again, very easy to prove. Doing the exact same thing, just opening up what V is, what W is, so this, yeah. Okay, and then over here we have some linear combinations of vectors. This is a little bit more relevant to multivariable, to linear algebra, so I'm not going to focus on this. It's not really relevant to multivariable, so there really is no point in focusing on the linear combinations part. but if you want to go over it with me at some point by yourself, just let me know. Okay, we want to talk about the unit vector a little. So the unit vector, or a unit vector, is any vector with unit length. So we want the magnitude of the vector. Second. Yeah. So we want the magnitude of our vector to be equal to 1. And if you think about this, as long as the vector lies on the origin, my unit vector is going to be in the unit circle. The x direction is going to have cosine theta, the y direction, the y component is going to have sine theta, because x is equal to r cosine of theta, and y is equal to r sine of theta. And r over here is 1, because our unit length is 1. So the unit vector can be given like that, cosine and sine. Of course, if you move it from the origin, then you're going to have a different vector. It's not going to lie on the unit circle, but you can, the vector will still be in this type of form. It just, its origin will be moved. So in general, if I give you a vector v, then the unit vector is the vector pointing in the same direction, but with unit length. Let's look at that. Any questions so far? Okay, so v is equal to v1 v2. Then we want to find a vector pointing in the same direction as v, but this new vector, let's call it, what do they call it? EV. Okay, for now we're going to call it EV. So if we just take our v and we divide by the magnitude of v. So the magnitude of v over here is the square root of v1 squared plus v2 squared. So if we just divide by the magnitude, so it's like we have a vector v, and we just multiply the vector by its own length. So we shrink the vector or expand it. So then now the vector is pointing in the same direction because the components over here are pointing in the same direction. But the magnitude of this is going to be 1. And we can actually see why that is. So the magnitude of EV is going to be equal. Now this is a scalar, so it can come up. So you can think about it as the absolute value. This is like your lambda. I'm not going to put an absolute value because it's positive. So this is the same as 1 over the magnitude of V times the magnitude of V, which is equal to 1. So this will give you your unit vector for V. It's pointing in the same, okay, second. Yeah, for some reason my pencil is not really working. Okay, I'm just gonna have to write on the whiteboard, I guess, until the pencil starts working again. If there's a way of making the eraser bigger. Okay. Anyone know how to make this is like Microsoft Whiteboard. Anyone know how to make the eraser here bigger? No. Okay. So another way we can look at V, if V is V1 and V2, it's going to be the magnitude of V. So this over here corresponds to this r right over here. And then you're going to have cosine of theta for the x direction. It's the x component, and this goes into the x component, and sine of theta for the y direction, because it's the y component of v. So, yeah, so that's another way of representing v. Are there any questions so far? So can I understand, like, I guess a lot of people have already seen this before, is that correct? Hello? Have you guys basically seen this stuff before, or is this new? And understood? Are there any questions? Anyone?
I've definitely seen it before in Physics 211, and I took Math 220, so that was a lot of this information. So if anyone took those classes, I think they definitely would know this stuff.
Okay, fine. So should I go faster?
I would
Anyone?
say keep this pace because I've seen it in physics, but I don't think it was explained very well in physics when I took it. So
Okay, I'll keep this. But it looks like my computer froze. Okay, so let's just try this example from now. So they want us to find the unit vector in the direction of v, and v is equal to 3, 5. So my v is equal to 3, 5. So the unit vector in that direction is going to be 1 over the magnitude of v times my v. So what's the magnitude of v? So it's going to be 3 squared, which is 9, plus 5 squared, which is 25. And then, so this is going to be the square root of 24. Let me see. This is, oh, sorry, 34, for 1 second. For some reason, this is not working. Yeah, sorry, 34. So now this is going to be 1 over the square root of 34. And then my vector here is the vector 3, 5. And I can put it inside, and it will give me 3 over the square root of 34, 5 over the square root of 34. Okay. It looks like my computer froze. It did. Hold on a second. Fine. So another way of looking at vectors is with I and J. Okay. Looks like my computer has frozen and I cannot really continue. So I think we should stop here. And by next time, I'm going to try to, yeah, I don't know why this just froze, but I can't continue. Let me try one thing. 1 second. Okay, that's good. Works now. So There's another way of representing vectors with I and J. So if you are in R2, so here we're in R2. Now you can think about I as the unit vector in the X direction. So it's the vector 1, 0 in the X. So it's just 1 in the X direction, 0 everywhere else. You think of J as 0, 1. And then if you want to look at a vector V, so let's say V is equal to AB. Well, this is the same as saying AI plus DJ. So the reason for this is because of you can take out the constants for A and for so again my V, let's say, is AB, then V is also equal to AI plus BJ. Why? Because this is equal to A, and then you have a 0, 1 over here, plus B, and then your J is 0, 1. And then this thing is going to be equal to A0 plus, plus 0B. And then this is equal to AB, which is equal to my V. So it's just another way of looking at vectors using unit vectors. So these problems with cables and all that, they're physics problems. The idea is basically to break out the components of the force into the X coordinate and the Y coordinate. I'm not going to go over this problem because I don't think it's that relevant for multivariable. If you have done physics, you have seen it. There might be a few problems in homework like this, I'm not sure. But it's not very relevant. But if you do have questions about it, yeah, we can meet for office hours and go over these type of problems. A very important rule for vectors are the triangle inequalities, or just triangle inequality over here. So the magnitude of V plus W is less than or equal to the magnitude of V plus the magnitude of W. I would actually say this becomes, it's not that relevant in multivariable. It becomes more relevant in like advanced calc, real analysis. So I'm not, I don't think we're going to use the triangle inequality in multivariable. But it is important to know. The reason is that the magnitude of V plus W going in this direction, the length over here is obviously going to be less than first going along W and then going along V, unless V is this, for example, and W, so if V is one vector, and that's when the equality holds, and then here is W, then this will be equal. Otherwise, this over here is less than this. Okay, so in summary, the vector PQ is the vector that starts at P and it ends at Q, and that's the head or the tip. So like we've seen, here is P, here is Q. This will be the vector V starting at P and ending at Q. The components of this vector, in order to find this vector, you need to take Q minus P. So you're looking at A2 minus A1 and B2 minus B1. So E is equal to A1 B1 and Q is equal to A2 B2. Then PQ is going to be the vector A2 minus A1 in the first component, B2 minus B1 in the second component. The magnitude, which comes from Pythagoras' theorem, is A squared plus B squared if V is the vector AB. And this magnitude is the distance from P to Q, which makes sense. And then if you just have a P naught, it's the same vector at the origin. Not very important to like specifically remember that notation, I don't think. Adding vectors, you add the components. If you have a scalar, then the length is going to be the scalar times the length of the original vector, and you can put the scalar into each component individually. And then the unit vector is just 1 over the magnitude of the original vector times that vector. If you want to decompose your vector into the x-coordinate and the y-coordinate, then, like we said, cosine x, so this over here, v, is equal to v1, v2. You can think about it as xy. And we know that x is equal to r cosine of theta, where r is the magnitude of this vector, and y is going to be equal to r sine of theta. So then v1, which is my x, is going to be the magnitude of the vector, which is my r, times cosine of theta. And v2, which is y, is going to be the magnitude, which is r times sine. And then my unit vector is just going to be cosine, comma, sine of the angle. The angle is this angle over here. Sorry about that. It's the angle that the vector makes with the x-axis. And then we have ij, which are the unit vectors. I is pointing in the x direction with unit 1, and j is pointing the y direction with unit 1. And we have the triangle inequality. Okay, I think this is, let me just see. Yeah, so now we have exercises. I'm not sure which one of these appear, and well, I don't know how exactly. We'll probably go through a bunch of exercises. If you have any questions about specific exercises, please let me know. Okay, so are there any questions on what we did today? No, everyone's good?
On the website where we're doing our homework, do we have to do the 12.1, 12.2 learning curve things, or just the homework?
So for now, let's do the, these are like practice problems before. I think for now we can do it. And then in like a week or two, I might decide that it's only the homework. But let's do a few of them just to see how it goes. Okay?
Okay, thank you.
Anything else? Okay, thank you everyone. And again, if you have any questions or you want to meet for office hours or to talk about anything, let me know. Okay?